One or two videos ago, we did a simple physics problem where the equation of motion was a simple polynomial, and then we were asked to do various questions about it, like accelerations and things like that. I wanted to go back and do a similar problem, but this time using Numpy's built-in polynomial functionality. And a lot of packages like MATLAB and Python have this capability built in. And when dealing with polynomials, it's sometimes more useful than you would think. At least when I first saw this, I thought it was kind of a little bit simple and didn't really use it much. But I've run into cases where it was quite advantageous. And if we go on to more difficult tasks, like orthogonal collocation, these types of things will be useful. So let's just do a quick physics problem and just see how this works. So let's go on over to the notebook and let's zoom in a little bit as usual. And the problem is the position of an object is given by a polynomial here, and it's a third order polynomial with a cubic term, quadratic term, linear term, and no constant term. And the questions that we're being asked is to calculate the velocity as a function of time, the object's acceleration as a function of time, max and min velocity, the points where the object is moving backwards. Let's see what this one says. I can't read it quite. Find the times when the object returns to its starting point, and calculate the object's average velocity and average speed. And here we're meaning velocity in the vector sense, so the direction, is it going forward or backwards? The speed is just the absolute value of the velocity. So I've already done the imports here. So I'm importing Numpy as MP as usual, and I'm also importing the plotting library so we can actually visualize some of these. So let's execute that cell. And now it's really easy to do polynomials. Let's do those imports, and we just use the command poly1d, and then we pass into it a vector of the coefficients of the polynomial from the highest order term to the lowest order term. So the coefficients would be here, in this case 1, minus 15, and 54. So it's 1 comma minus 15 comma 54, and there's no constant term, so comma 0. And now we just close this, and let's plot this out and see what it actually looks like. So let's do that in a different, let's do it at the same cell here. So let's go plt.plot. Well, actually first we're going to need to know the time. So let t be np.lin space. Let's go 0 to 10 seconds, and let's explicitly set 100 points. And now let's do plt.plot t and x of t. So we're just going to pass in the time argument to our polynomial, and that it will evaluate that entity, that object, at all those points in time. So let's see what that looks like. So here we go. It's just a cubic polynomial that's kind of almost like a sine wave in appearance here. So it starts at time equal to 0, at position 0, rises up, turns around, comes down, and kind of does this oscillatory behavior. So let's go on now and do questions 1 and 2 here. So what's the velocity and the acceleration as a function of time? Now it's easy to calculate the derivatives of these things because it's just a formula. So that's automatically built into Numpy. So all we have to do is call the derivative operation on this function, and it will automatically calculate the derivatives. And the first derivative of x is going to be our velocity, and the second derivative of x is going to be the acceleration. So let's do that. So let's define a new variable, v, and that's just going to be the velocity, and that's the derivative of position with respect to time. So that's just x dot deriv. And the acceleration is the derivative of the velocity with respect to time. So a is just equal to v dot deriv. And that's all there is to that. So let's actually visualize what the velocity and the acceleration look like as functions of time. And I want to put these side by side. So I've never tried using the subplot, plt.subplot functionality within a Jupyter notebook, so I hope this actually works. You think I would actually try this out beforehand, but that would kind of be logical and make sense. So let's just see what happens. So I wanted to have them side by side, so one row, two columns, and the first plot And I'm just going to separate these with a semicolon, just put it all on one line. So plt dot plot t comma v of t. So that's our velocity, and I'm just going to put plt dot title on here just to be clear, velocity. And let's do the same thing for the acceleration. So plt dot subplot 1 comma 2 comma 2, our second plot, and do plt dot plot t comma a of t. And let's also put the title on here. So plt dot title acceleration. Okay. I really butchered the spelling of that, didn't I? Acceleration. So let's see if I actually did this correctly, and I did not. Oh, I have a typo here. Plot. So there are two plots. Not surprisingly, the velocity, since the position is a cubic as a function of time, its derivative is a parabola. It's a second-order polynomial, and the acceleration is linear. Right? Two derivatives of a cubic is a linear. So there we go with those things. Now let's go on to the next one. What's our next question? The maximum and minimum velocities. Let's go down here. We can get an estimate of the minimum velocity just by printing out, and this is not probably the best way to do it, and I want to demonstrate more polynomial type functionality, so this is not how we're going to actually do it. But we could pass in the velocity as a function of time to the min function, so it's just going to be an array, and it's going to find the minimum value of that array. So we could go np dot a min v of t, and theoretically that'll work. So that's a number we get there. So let's go back up here, and we'll use the roots function. So remember, to find the minimum of a function, we can just take its derivative, find the root of its derivative. So it's going to be at the point, the derivative of the velocity of acceleration. Where does the acceleration go to 0? So what we could do is say we can create a variable called t underscore min and set that equal to the root of the acceleration. So a dot r, and it's going to return a vector. So let's just pull out the first element. It only has one root, so it's not really an issue, but just do that. And let's just print out that value, t underscore min. Let's see if that's doing it. So 5 seconds, does that make sense with our times here at 5 seconds? Yeah, it looks like it crosses 0 at 5 seconds. So let's plug t equals 5 seconds into the print v t min. So hopefully that'll give us the velocity at 5 seconds, which should be about minus 20 something, which should agree with roughly this value there. And there we go. So about minus 21 here, about minus 21 here. We are good. So next question. Maximum velocity. Actually, I did these out of order. Okay. Oh well. Now let's do the maximum velocity. So we can see that this function is not going to really have a maximum. I mean, it has a maximum within the time interval that we have plotted here. So it's going to have an answer about 50 something, which is what it wants. But this function is not going to have an actual maximum where we can find the derivative, set it equal to 0, and do all that. So here we can just do what we did above with searching the array for the max. So let's just go print np.amax v of t. So 54, is that about right? That looks about right here. So okay, we're good there. Next question. Find the times when the object is moving backwards. So when the velocity is less than 0. So again, here we're going to use the roots command, and I'm going to do this in a different cell here. So we want to find the times when it's moving backwards. So we need, since it starts off as a positive value, we want to find basically where this thing crosses 0. So these times here, and that's just the roots of the polynomial. So we can print v dot r. So 7 something and 2 something seconds. So about 2 seconds, that looks about right. 7 seconds, that looks about right. And let's just actually sort this. So let's go np.sort. What happened? Am I missing a parenthesis? I'm missing a parenthesis. So there we go. Now it's in the right order, just to be clear, right? It goes 2 seconds first and then 7 seconds. So the next question is, when does the object return to its starting position? Again, this is just the roots of this equation here. So it starts at 0, so when does it cross 0? Again, that's just the roots of x. So let's just go down here and print x dot r. So it's 6 and 9 seconds. 6 and 9 seconds. That looks about right. Again, we could sort this just to make sure that it kind of makes sense chronologically. So np.sort. So there we go, 0, 6, 9. Okay. Last two questions. Calculate the average velocity and the average speed. Okay, so the average velocity, again, this is easy. This is just the integral of this velocity function from 0 to 10, and then we just divide by this interval, of 10 seconds. So just like we can calculate derivatives, we can calculate integrals. So we can calculate v dot integral, and we can evaluate that at 10 seconds. And then just to be clear, make this kind of a little more rigorous, we can evaluate the integral of this at 0 seconds. So it's like the definite integral. So int eg 0, and then we have to divide this by 10. So let's wrap this in parentheses and divide by 10. And something looks a little off here. First I need a close parenthesis. Oh, and this is a function. This intg thing is a function, so we need to have the open and close parentheses, and then we're taking the evaluating that result at 10. So let's just write this in a print, and let's go. Oh, there's an error, of course. I think I'm missing a parenthesis here. Okay, 4. There we go. And we can also do this numerically. We could just take that, we can also approximate this numerically at least. We could take that time vector and do the numerical integration with the trap z command. So let's just do that and see what we get. So let's go down here, print. Let's take v of t. Actually, let's integrate it. So it's np.trap z. It's v of t, and remember this is the backwards of MATLAB, so t, and then we have to divide that by 10. And have I done everything correctly here? I am missing a parenthesis here, and hopefully that'll run, and it does. And there we go, and we get the same answer. Not surprising. And for the average speed, I mean, you could be cute and kind of flip this kind of negative portion down and, just integrate from t equals 0 to where it crosses that first root there. Then integrate from that first root to the second root, take the negative of that, and then, finish from the first root to 10 seconds, and then add the 3 together. But this is running longer than I wanted to, and it's already pretty simple. So let's just do this. Let's just copy this. We'll even do it in a new cell. We'll paste it down here. And what we'll just do is take the absolute value of this, np.abs, the absolute value, and that should do it. So that's it. Again, this is just a quick video showing how Python's polynomial functions work. Again, it's something that these problems are really easy. However, this does turn out to be useful in certain cases. So I just wanted to make sure I had covered it at some point. Until next time, later.